Hello and welcome to Gurukul Bytes. In this video, I'll be discussing problems based on one particular pattern that can be solved using binary search application. So basically, I'll be discussing one problem in detail and three follow-up problems. And once you learn how to do them, you'll be able to solve many more problems which follow the same pattern. So let's start with the first question. Find first occurrence of an element in a sorted array. So let's say we have two example arrays and the element that we are searching for is 8. So the first occurrence of 8 in array 1 is index 1, and in array 2 the first occurrence of 8 is again index 1. So the expected output in both the cases is index 1. So one way to do this is obviously sequential search. You start traversing from the left. As soon as you find or encounter the element that you are looking for, you return that index. But the time complexity in sequential search would be order of n. And we want to explore if this can be done in less than order n. So less than order n mein one algorithm which comes to our mind is binary search. So एक बार binary search apply करके देखते हैं what is the result that we get, and then we can proceed from there. So binary search is basically we calculate the mid index and then we try to match it with the search element. If the match is successful, obviously that is the returned answer. If not, then we try to analyze if the solution lies in the left half or the right half. So let's say in array 1, the index, mid index would be leftmost index plus rightmost index by 2, which is 1 in integer value. And then binary search would try to match the element present at index 1, which is 8, with the search element. So the match is successful here. So the answer returned would be 1, which is also the first occurrence. So array 1 mein simple binary search gives me the first occurrence of 8. Let's see if the same is followed in array 2 or not. So array 2 mein mid index comes out to be leftmost plus rightmost index divided by 2, which is 2. Again, binary search tries to match the element present at second index, which is 8, with the element we are searching, 8. Match is successful. So in this case, binary search would return index 2. However, this index 2 is not the first occurrence of 8. So binary search say we do get one occurrence of the element inside that array, but that occurrence is not necessarily the first occurrence, right? So before I proceed further, I want you all to think of a solution which is better than linear complexity, of course. So pause the video right here and play when you're ready. All right, so one solution, one approach which lots of students come up with is, first you apply binary search to get any occurrence of x, and then you check if it's the first occurrence or not. If it is the first occurrence, you get the solution. If it is not the first occurrence, then you traverse left until solution or the first occurrence is found. So let's say in the first array, binary search gave you index 1. Then you check the element on its left, which is 2. 2 is not equal to 8. So this means index 1 itself is the first occurrence. So you return 1. Fine. In the second array, binary search gave you index 2, which is element 8. Then you check the element on its left, which is also equal to 8, which means index 2 is not the first occurrence, so you start traversing on the left until the first occurrence is found, which is index 1. So in this case, again 1 is returned. So let's try to analyze the time complexity. So first we apply binary search in login, and then we take some steps or traversals on the left, which we can denote as some constant traversals. So this time complexity comes out to be equal to order of log n. Now let's try to analyze the worst case scenario that can happen, and if this still holds true in that case. So for that, let's consider this example, and let's assume all these dots are nothing but elements filled with value 8. So in this case, the value of mid comes out to be equal to leftmost plus rightmost divided by 2 n by 2. Then you check the element at n by 2 index, which is 8, and then you check if this is the first occurrence or not. So for that, you compare it with the left index. That is also equal to 8, which means this is not the first occurrence. So you start traversing left until the first occurrence is found. In this case, there is no left element once you reach the index 0. So you can say the solution is 0th index, or the first occurrence comes at 0th index. So in this case, if we analyze the time complexity, then log in steps for the binary search, and then how many steps we had to take on the left? N by 2 steps. And this is equal to order of n. So here we cannot write the time complexity as order of log n, since in the worst case the value of c comes out to be equal to n by 2, which makes the time complexity of this algorithm as worst case time complexity as order of n. So let's try to, all right, so in the previous video I had discussed, if you want to solve a problem using binary search application, then you need to follow certain steps or rules which binary search itself follows, due to which it achieves a time complexity of order log n. So if you want to know in detail, do watch out that video. In this video also, I'll quickly go through the steps once again. So what happens in binary search is you go to mid, you check if mid is solution. If mid is the solution, then you exit happily. If it is not the solution, then you try to establish if solution is in one half, either the left half or the right half. So once you know if solution is in one particular half, then you confine that subarray, and then you perform all the steps in that, repeat all the steps in that subarray. You go to mid of that subarray, and then you check if that is the solution, and you keep on doing this until the solution is found. And all these steps, all these checks, you have to perform in constant time. Otherwise, the time complexity of order log n would be compromised. So let's see in the previous case where we deviated from this approach. So we did find the mid element. We did check if this is the solution or not. It wasn't. So what we had to do was, if this wasn't the solution, we had to establish if solution is in one particular half. So in this case, we can definitely say if this is not the solution lies in left half for sure. Instead of that, what we did in this approach was we started traversing linearly, which is why in worst case, we got the time complexity of order n. So let's try to form all the cases and derive the solution from there. So to solve this problem, you first calculate mid and then you find the mid element and then you compare the mid element with x. So there are three possibilities. Either x can be equal to the mid element, or x can be less than the mid element, or x can be greater than the mid element. And then you want to find the solution. All right. Now, since the array is sorted in increasing order, this is a mid. All right. Now, if x is less than a mid, we can definitely say the solution lies in left half, right? And if x is greater than a mid, we can say solution lies in right half. Let me just, all right. And what if x is equal to a mid? So if x is equal to a mid, like in both these cases, then we need to further check if that is the first occurrence or not. And whether the mid element is first occurrence, for that we need to check the element on its left. So left element, which is nothing but a of mid minus 1. So if x is equal to a mid, then we also check the left element. Now for the left element, what are different possibilities? One possibility is there is no left element at all. Let's say the sub array is just this, just a single element. So the value of L and R both are 0. In this case, the value of mid comes out to be 0 plus 0 by 2, which is 0. And mid minus 1 does not exist. So one possibility is this. Then other possibility is left element is equal to x. And the other possibility is left element is not equal to x, right? So if x is equal to a mid, if x is equal to mid element and there is no left element, we can definitely say that mid is the solution. Since there is no left element, that obviously means mid is the first occurrence. If x is equal to a mid and left element is also equal to x, this means, like in this case, x is equal to a mid, but the left element is also equal to a mid, x. So in this case, we can say that the solution lies in the left half, right? And if x is equal to a mid and left element is not equal to x, then we can say that mid is the solution, right? So once we've known this flowchart or once we've analyzed all the cases, it's very easy to code now. So let's code int first occurrence, array as an input, subarray is defined by left index, right index, and we also given the element x which is to be searched. Then in binary search, what we do is if left is less than equal to r, if you are not so well versed with binary search algorithm, again do check out the previous video. Then mid is calculated by L plus R minus L by 2 instead of L plus R by 2. Again, detailed explanation is in previous video, but the concept is L plus R by 2. It's the same thing. L plus R by 2 and L plus R minus L by 2. These are the same things. But in L plus R by 2, L plus R can exceed um, the integer value. It can overflow, which is why we write it as L plus R minus L by 2. So then we write all these cases here. That's it. So if x is double equal to a of mid minus 1, sorry, a of mid, then there are three cases. No left element. No left element means if the value of mid is equal to 0, then there is no left element. In this case, the answer is mid itself, right? Then the next case is if the left element is double equal to x. If the left element is double equal to x, then the answer lies in left half. So let me just write left half for now. And if left element is not equal to x, then also the solution is met. Right? So we've written the code for case 1. Now, if x is less than a mid, then answer lies in left half. If x is greater than a mid, answer lies in right half. And if left is not less than equal to r, then we return -1. Why? Because if left is not less than equal to r, then it does not represent a valid subarray, which means that the element which we were searching for doesn't occur in the array. All right, so if the solution lies in the left half, so if the solution lies in the left half, what we need to return first occurrence A. All right, now check this array once again. This is mid element, this is L, this is R. The element on its left is mid -1, and this is mid +1. So if the solution lies in the left half, then the subarray can be denoted by L comma mid -1. Element to be searched is X only. And in this case, it can be written as return first occurrence. The right half can be denoted by mid +1. The left index is mid +1. The right index remains R and X. All right. So that's the solution. Now you can further optimize this code, but at least this will give you the solution in all the cases, and the time complexity will remain log n in all the cases. All right. Now, if you understood this problem, there are several other problems based on the same pattern, which now I think you would be able to solve in a much more easier way. So the next question, let's take the next question. Find last occurrence of an element X in a sorted array. So previous question was first occurrence. The only change is instead of first occurrence, we have to find the last occurrence. So I leave this problem to you to solve. Try building the solution from the scratch, as in step by step, and you'll understand the changes in code that are required. All right, the next question is search for an element X in a rotated sorted array. So for that, let's try to understand what is a rotated sorted array. So, all right. So a rotated sorted array is if I break this array into two sub arrays and then I rotate this first sub array like this, then this becomes a rotated sorted array. So this is a rotated sorted array. So what we have to do is we have to search for an element X in this rotated sorted array. So how do we do that? So again, pause the video once again, think of a solution, think of an approach in less than order n time complexity. Again, sequential search will give you order n, but we want to solve it using binary search approach. So pause the video and play when you're ready. All right, let's look at the solution now. So if you look at this array, rotated sorted array, one thing you can notice is that the numbers keep on increasing, and then after 72 it suddenly drops and then it increases again, right? So I can say there is a fall that happens, and this, let me call this element 2 as the break element. The first element that occurs after fall, that is the break element. All right, so one approach is, let's say I find this break element, find break element, and then I divide the array into two sorted sub-arrays, and then I can search for X in the sub-arrays using binary search, right? So as you can see, a rotated sorted array is nothing but a combination of two sorted sub-arrays. And if I somehow find this break element, then I can divide this whole array into two sorted sub-arrays, and then I can search for element X in this sorted array using binary search. Also, I can find for element X in this sorted array, and then I can get the solution. So this step 3 can be done in order of log n, binary search in a sorted array. If I want this whole solution to be done in order log n, then step 1, which is finding break element, that also has to be done in order log n. So if step 1 can be performed, we obviously know how to reach the solution. So now the question has changed, and now the question is Find break element in a rotated sorted array in order log n. If I can find this, if I can achieve this, obviously I can solve this question, right? So now forget about the previous question. Now we just have to find the break element in a rotated sorted array in order log n. And also let me copy this array and paste it here. Okay. All right, so now I have to find this break element in a rotated sorted array in order of log n. So again, one thing which I can notice is that the break element, that the left neighbor of the break element is greater than the break element. So one observation is left neighbor of break element is greater than break element. Otherwise, the elements keep on increasing and it's only at the break element that the left neighbor is greater, else the numbers keep on increasing. The other pattern which I can notice is so let's say I call it fall and I call these elements after fall elements and these elements I call before fall elements. So another thing which I can notice is that all the after fall elements are lesser than before fall elements. Why? Because this was originally a part of this array when the array wasn't rotated. So let me just write it down. After fall elements are lesser than before fall elements. Right? All right. So if I want to do this, if I want to achieve the solution in log in time, then I do get a hint that binary search approach has to be applied somehow. And in binary search approach, what you do is you go to mid element, check if mid is solution. So let's go to the mid element in this array. Let's just number it, give them the indices. All right, so in this case, the mid element is 0 plus 7 by 2, which is 3. So 23 is the mid element here. Is it also the break element? How can we check? If this was the break element, its left neighbor would have been greater, which is not. So this is not the break element. So I can also write the condition to check if mid is solution. If mid is solution or mid is break element, then A of the left neighbor has to be greater. If this is the case, then we return mid as the answer. So one condition we know now, although in this case 23 is not the solution because the left neighbor is smaller. So now can we know, So 23 is not the solution. But now can we know somehow if the solution lies in the left half or the right half? Is there some condition that we can check to say whether the answer is in left half or right half? And if there is, what is it? So one another thing which I can say is that 7 is for sure a before fall element, right? Because the array starts, it's the leftmost index of this array. So 7 is definitely a before fall element. And we were at the mid element. We checked that the mid element is not the solution. And now we want to establish if the solution lies in the left half or the right half. So one thing which you can observe is that 23 is greater than 7, right? 23 is greater than 7, which means that the fall hasn't happened. Because if 23 was an after fall element, then all the after fall elements are lesser than before fall elements. In this case, 23 is greater than 7, which means the fall hasn't happened yet, which means the fall will happen in the right half. And since the fall will happen in the right half, the break element also lies in the right half. So now we know the condition for the break element as well, that if A of mid is greater than A of L, the leftmost index, then solution is in right half, else left half. And these are the conditions we need to know to write the whole code using binary search approach. So let's just try to dry run it. So in this case, 23 is greater than 7, which means the fall hasn't happened yet. And the break element is in the right half. So now we confine the sub array to this much part. And now we calculate the mid of this sub array. So the mid of this sub array would be 4 plus 7 divided by 2, which is 5 in integer value. And the element at this mid is 2. So now we check if mid is the solution or not. For that, we check the left neighbor, which is greater than 2 in this case. So we return mid as the answer, which is element 2 or index 5, right? So let me take another example, and I'll just dry run this whole algorithm on this example again. So as you can see, this is a rotated sorted array. So the elements increase and then there is a fall, and then these elements increase again, and all the after fall elements are lesser than before fall elements. This is 23, this is 12, this is 2, this is 72, right? And we have to know the break element in this, which is 2. So let me give these indices, right? So the mid element would be 0 plus 7 by 2, which is 3. So now I check if 3 is the solution. Is the left neighbor greater than 3? No. So that means 3 is not the solution. Now we try to understand if the solution lies in the left half or the right half. For that, what do? We compare the mid element with the leftmost element. So we compare 3 with 23. If A of mid, if 3 is greater than 23, 3 is not greater than 23, which means the solution lies in the left half. So now we confine the solution subarray to 23, 72, and 2. And then we calculate the mid again. 0 plus 2 by 2 is 1. So the mid element is 72. Is 72 the break element? The left neighbor has to be greater than 72, which it is not. So 72 is not the break element. Now we check whether the solution lies in the left half or the right half. Now 72 is greater than 23, which means the fall hasn't happened yet, which also means where will the fall happen? On the right of 72, which means the break element also has to be on the right of 72. Now there is only one element on the right of 72, which is 2. And for this, when the subarray is confined to this, we just check if the element on its left exists and is greater than 2 or not. So it does exist, and 72 is greater than 2, which means 2 is the break element, right? So I'll not write the code for this one. I'll let you write it. If you have any question, do comment on the video below. And I think now you would be able to solve any other variant of searching problem using binary search based on the same pattern. So that'll be it. Thank you.